Now see a nuclear density. Nuclear density is actually defined as the mass of the nucleus divided by its volume. So we can write nuclear density is equal to mass of nucleus divided by volume of nucleus. Now we know it, volume we can write, volume is equal to 4 upon 3 pi r cube, and mass of nucleus we can assume here, let mass of a nucleon be m. So nucleon is actually number of protons and number of neutrons. We have assumed here the equal masses. So total mass of nucleus, that is equal to here mass number into this, so that is A into m. Now we can write, this is the total mass of the nucleus and this is the volume. So we can write here now the nuclear density is equal to Am upon 4 upon 3 pi r cube, where r is the radius which already we have calculated. R is equal to r naught a raised to power 1 upon 3. So we can write nuclear density is here, that is equal to Am upon 4 upon 3 pi r naught cube into A. This A and this A cancelled. So we will be getting nuclear density is equal to m upon 4 upon 3 pi r naught cube. Now see, a very important step is here, the nuclear density does not depend on the mass of the mass number of the atom. It is independent of the mass number of the atom. It means approximately all the nucleus have got the same nuclear density. So we can also calculate this. So we can write here nuclear density is equal to, if I put all the values, mass of a nucleon, that can be written 1.67 into 10 raised to power minus 27 kg divided by 4 upon 3 into 3.14. R naught value we know it, that is 1.2 into 10 raised to power minus 15 cube. When we solve it, so this will be getting here kg per meter cube, and here we can write, by solving this, 2.29 into 10 raised to power 17 kg per meter cube. So this is approximately order of the nuclear density. But the very important thing is here, the nuclear density is independent of mass number. Now see here, these are the three different terminology here: isotopes, isobars and isotones. And in the first one is here isotopes. What are isotopes? So in isotopes, basically we take elements whose atomic number are same but mass numbers are different. So if you take example hydrogen, hydrogen has got the three isotopes like 1H1, 1H2 and here 1H3. So these are the three isotopes of hydrogen. In all these three cases, atomic number remains same but mass numbers are different. Similarly, we can take here another one, that is isobars. In isobars, what happened here? In this case, atomic number is different but atomic weight is here, that remains same. Example, we can take here like Na and another one is Ne. So in these two elements you will be seeing here, atomic numbers are different but mass numbers are same. That means atomic weights are same. Third one is here isotones. We can write, in isotones, here we can take actually the element which has got the same number of neutrons. So if you take the example like a chlorine here, this 17 here and this 37, and then we can take potassium, that is K39 and 19. In both these elements you will see here atomic numbers are different, but if you calculate number of neutron, that is A minus Z, you will be getting equal. So A minus Z is equal to number of neutron N, and this N is equal, number of neutrons are equal in these two cases. So this is actually, these are known as actually isotones.